Okay, can you hear me all right? Yeah, that's good. I'm quite quiet, so I'll try and talk close to the speaker. But thank you for coming. This is my talk, Technical Archaeology. So to give a bit of explanation of the talk, a bit of background of who I am. My name is Sarah Saunders, and my title at Capgemini is a senior developer. I've been working in IT as a programmer, as an architect for 15 years. 8 of those have been at Capgemini. And it's made me kind of a jack of all trades, master of none, but it's given me quite a unique perspective on technology because, you know, I've moved projects regularly over the years. I've worked with different languages, different stacks. I started off as a Java developer, and I started off mainly doing web development. So this does come from a kind of web development perspective. Most of the things that I've built have started with some kind of client and a browser and ended with some kind of data source. But I think that my observations are probably relevant across other technologies as well. And this talk sort of came out of a series of bugbears that I was constantly having in my work, and me stopping to think, well, how are these related? And sort of, it's a step back. It's different probably from some of the other talks you've been to today because it's looking at old stuff rather than modern stuff. But sometimes it does you a good job to step back and sort of say, how did we get here, and how did the architectures that we've built evolve to where they are today? So for the agenda, as I said, I want to talk about the evolution of the architectures that we had. So I'll introduce some evolutionary concepts that I'm going to link to technology. And then a quick history of distributed architectures. How did we get to where we are today? And then we'll go on a dinosaur hunt, and I'm going to find some examples of architectural dinosaurs that we have hidden in our stacks today. Stupidly, I've got a couple of demos that I'm going to try and run just to break it up a bit. They're not necessary, but hopefully they'll work. And then some conclusions. So as I said, I want to talk a little bit about evolution. I don't know much about biological evolution, so I'm not going to go into great depth, but there's a few concepts that I want to bring out. And the first salient point, when the Victorians started studying evolution, they believed that it was convergent, that we were converging upon some form of perfection. They would say man is becoming closer to the image of God. And now we know this isn't true. Evolution is not convergent. It is divergent. Species adapt and change based on the environments that they live in, and as those environments change, it triggers further change. So as an example of divergence from the biological world, let's look at the seal. The picture in the top left there is a creature called the Tiktaalik that lived something like 45 million years ago. And it's suspected to be the ancestor of all mammals. It was a fish, it had gills, but it also had lungs, and its fins were strong enough that it could drag itself onto land. Fast forward to the bottom picture here, I think that's about 2.5 million years old. It's also an ancestor of the seal. I forget what that one's called, Pugilia or something. And you can see it looks more like a dog. It's got fur, it's definitely got legs, it looks like a land animal. And then we fast forward again to the picture in the top right. The seal today kind of looks more like its ancient ancestor. It's smooth-skinned and flippered once more. The seal is not converging upon anything. It's adapting to where it can be most successful and where it can survive. And I think we also have divergence in our technical architectures. An example could be the famous macro versus microkernel debate from the early 90s. Most of the operating systems that we use today were built in the early 90s. And at the time, the arguments as to whether you should use a monolithic kernel or a microkernel, were not clear cut. I don't know a great deal about kernel architecture, but I believe a monolithic kernel kind of exposes the operating system functionality as a kind of black box, whereas the microkernel is more pieces that you expose one by one. And at the time, the monolithic kernel arguments were slightly stronger, and things like DOS, Unix are built on a monolithic kernel architecture. But that may not always be the case. QNX, which BlackBerry runs on, is a microkernel architecture. So just because that decision was made in the early 90s doesn't mean the end of the concept of a microkernel architecture. It was just at that time. So that was divergence, the first concept I wanted to introduce. And this is a picture of some goosebumps. Goosebumps allegedly have two functions in mammals. They raise the hair follicles to allow a layer of air to be trapped underneath to help for insulation. And they can make the mammal look larger to scare away predators. They don't really achieve either of these functions in humans anymore. We don't really have a big, shaggy enough coat for either of those to work. But we still have the goosebumps, and that's because they're not slowing us down in any way. There's no reason for them to be kind of evolved out of our bodies, so we still have them. And they're called vestigial functionality. And I believe that we have vestigial functionality in our architectures today. There's a lot of things that we do because we've always done them. We don't stop to think, is that actually relevant anymore in the environment that I'm designing for? So those are the two evolutionary concepts I wanted to define. I've got divergence and vestigial functionality. And then just the last thing before we look at some dinosaurs is a brief kind of thinking about, well, where have we come from and why? So the where bit, if I look back at the sort of evolution of technical architecture, there are two very strong drives that we can see. The first is distribution. When we started with computing, we'd have a single big mainframe, and then advances in interfaces allowed for things like keyboards and screens, so that we could talk to them without using punch cards. And then the cable between the screen and the mainframe gets longer and longer, and then you have client-server architecture. And then we branch out onto the internet and have multiple clients for a single server. So we end up with a service-oriented architecture with a middleware layer to deal with multi-threading and things like that. And then with the advances of things like 4G, optical fiber, you know, the network is no longer such a drag as it was in early architectures. So we've got things like microservice architectures being enabled, and then the concept of the cloud as well. Cloud architectures have been enabled by developments in networking. And then another very strong drive that we can see is miniaturization. From the mainframe, we went to the desktop PC. And Microsoft had a very strong role to play there in ensuring that we could all have a copy of our company's business logic on our own desktops. In retrospect, maybe not such a good idea, but miniaturization has continued since then until today. The smartphones that we use have the same computing power as the mainframe that sent Apollo to the moon. So a very, very strong drive in that direction as well. And why have things changed? I've sort of categorized the reasons that we've gone in these directions into two groups. The technical group, by which I mean advances in hardware, things getting smaller, batteries getting more powerful. Advances in design, you know, even things like, you know, understanding methodologies, you know, has enabled us to build more complex architectures. And algorithms as well. For instance, compression algorithms have been incredibly important in things like moving images around the internet. So as these technical developments advance, it allows us to build different architectures using them. And then there's a kind of social aspect as well. I called it social, I don't know if that's the right word. But things like, we've seen it before with Sony back in the old Betamax days, and they've tried again with Blu-ray, a large company using its marketing and selling power to push forward something which may or may not be the best way to do things. And policies and laws, an example of this might be California outlawing the use of Google Glass in public places, Germany outlawing the use of Uber. Standards and protocols, things like the WC3, when they come out with a new standard, it affects how we build. If they haven't come out with a new standard, people are less likely to take up, you know, different ways of doing things. So those are very strong social drives that help us define our architectures. And then the sort of cultural drives I've put. I think we've seen this a lot with things like social networking. People are quite slow to pick up new things, quite nervous of trying new ways of doing things. But then once there's got that sort of group confidence that, yes, this is okay, then suddenly it becomes the norm. So you'll see the curve of take-up of things like, social media sites really, really steeply climbing as it suddenly becomes socially acceptable to act in these ways. So these are the drivers that have changed our architectures over the years. So with these concepts in mind, we've got divergence, vestigial functionality, and understanding that things are changing because the environments are changing. We can go on our dinosaur hunt. I've got 5 dinosaurs to reveal to you today. We'll start with this likely looking spot to dig. And the first dinosaur that I want to talk about is the Singleton Pattern. So a brief definition, the Singleton Pattern ensures that only one object of a particular class is ever created. All further reference to objects of the Singleton class refer to the same underlying instance. Where do we use it? We use it all the time. If ever you're asked, well, certainly if you learned coding in the 90s or noughties, if you were asked to build a thread pool, a database management system, anything that deals with configuration or a connection to external resources, the first thing that might come into your head would be the Singleton pattern. You'll say, all right, well, I'll control this with a singleton. But sometimes I think we might end up just doing it out of habit without stopping to think, actually, is this relevant to my architecture? If you think a bit more about the Singleton pattern itself, its design very much lines up with a single CPU, PC hardware concept. You've got your threads running, but they're talking to this one piece of static data. It's object-oriented, almost by definition. Inherit interface, I can't remember what that would mean. I think that's why you don't use a singleton as a out-and-out static class, because you can therefore inherit from it, which you couldn't do if it was simply static code. But the problems with the singleton, for number one, multiple CPU architecture blocker. As soon as you've got this single point with multiple threads talking to it, you've got multi-threading issues, and they're not easy to resolve if you're doing functional programming. You should have this concept of immutability. You shouldn't be allowing this kind of structure. If you've got a message-based architecture, where's your static code? I mean, we saw this at Capgemini, where we were given a Java library to use on an ESB, and they were sure that they had no static code within it, but they had singleton patterns scattered through it. So, of course, it wouldn't work on the ESB because there is no single point for the singleton to reference. And you can't mock test it. I put that because you can't, there is no interface to the singleton. By definition, it has this static code, so you can't create a mock version of it. And my other beef with the singleton pattern is that there are many much more reasonable alternatives. The Spring singleton bean is not implemented using a singleton pattern. So this concept that Spring used, inversion of control with the configuration rather than static code, is a much better way if you want to control how many of these objects you're creating. Or implement it as a service in a microservice architecture. The singleton should just manage itself. It shouldn't be using static references to control how people use it. And constructor parameters, what I mean by this is sometimes people will say, oh, well, I've used this as a singleton because you should never create more than 10 threads. Leave that a little bit up to the developers. Put it as a parameter in a constructor for the class and let the people using the libraries decide, rather than you imposing your thoughts by restricting using the singleton pattern. So I'm branding the singleton as vestigial. I think we use it regularly, but we probably should think again in modern architectures about whether it really is the right pattern to use. Next likely piece of ground to dig on, ORM. So object relational mapping. I was in two minds as to whether to put this in, because it's not that I don't appreciate the skill of people that write ORM libraries, the power of the libraries, and I also didn't realise that ORM bashing is basically a conference sport. But in the end, I've decided that I will put it in because I think it fits with the themes that I'm coming from. The quick definition here, so it's a programming technique for converting data between incompatible type systems in object-oriented programming languages. And if you've ever seen any SOA stack, it will probably have an ORM layer. In the Java world, we use Hibernate a lot. In the C# world, they use Entity Framework, ASP.NET. And it's a wonderful thing. It abstracts from the developer all the hard work of matching up what's in the database with what's in memory. But then what you find is you forget about all the wonderful stuff it's doing and you start to abuse it. The architect will say, yep, stick ORM in there, and the developer will say, oh, I need this object and I need this object, whereas under the covers, they've lazy loaded half of the database into memory and they've got these, chains of reference, and the DBAs are complaining that they've lost ability to tune the schema. And as I say, you've hidden the complexity of what's going on. You've lost track of, well, what is the actual data that I want to send across to the database? And I don't think that's something that we really should be abstracting. It'd be better to simplify our architecture to have the developers really understand, okay, what am I updating here? What are the consequences of me, referring to this object? And then the other point about using ORM is you're kind of losing some of the power of modern databases. Databases today, they speak XML, they speak REST. You can just reference them as a service in a microservice architecture. There's no need to abstract their power with an ORM library. And as I said, the obfuscation that will imply. So again, for this reason, I'm branding ORM as vestigial functionality. It sort of harks back to the days when we had a fairly simple 3-tier stack and we were trying to reduce network performance by keeping a lot of the database in memory. And these days, that might not necessarily be the right way to go. So, architects, don't just whack it in there every time you see a database. Have a think about exactly what does it do, and am I going to benefit from including it here? Right, third place to dig, cause. So I'm going to try and do a demo here to show how the hip young developer of today, such as yourselves, might come across cause. So say, you're waking up doing your hip young developer things, you have a fight with some hair products, you down your protein shake, off to the office. First message in your window, dear hip young developer, please can you design for me a high performance, scalable, resilient, RESTful dinosaur management service. So you say, sure, yeah, I can probably knock that up this morning. And the first thing you would do is you would head off to something like TypeSafe Activator. So I'll just, I don't think I've started it here. And what TypeSafe Activator will do is provide you with a number of templates to get you started. So you're saving time, you're not going to be writing too much code. And here we are. Here's some templates. Let's have a look at this one. A REST API for the CRUD operation of a widget. Sounds perfect for us. I don't think I really want to run it in Internet Explorer. So we'll start that. We'll have a quick look at the code. So, no, not that one. This has been written in Scala using a package called, or a library called Spray, which, if you've ever seen it before, is an excellent way to write web applications using Scala. It's got some lovely language features, directives. It makes it incredibly easy to read. So you can see here, I've changed everywhere it said widget, I've changed it to dinosaur, but that's the only change that I've made from the template. So we've got our model, so we can say, I've got the concept of a dinosaur. It might have a name, an era that it lived in, whether or not it's a carnivore. And then we have a service, and the services are going to act as the front end for our RESTful dinosaur access. So you can see here, we've got this nice routing, so you can see I've got get, and I've got post that's going to create my dinosaurs, put to update them, and delete. And that will pass the message through to a dinosaur handler, and then under the covers it will use actors to separate out the work of persisting these dinosaurs. So let's just see if TypeSafe has started it for me. Yeah, and we'll just check it's running. I think it's on 90, 92. Great, so there's our empty array of dinosaurs. Well, that's that done. I can go for my developer lunch. And so the developer comes back having done his lunch activity, he's gone to the gym, posted his post-workout selfie, and he's ready for the afternoon. Dear hip young developer, thank you for that, but I need a front end. Oh, have to give up my afternoon job as a barista, but I can probably knock that up for you. So what do? They need another template. They'll probably use something like AngularJS, which comes ready packaged with a web server. So all I have to do is use Node to deploy it. I can start it up here. And then the template that I've got from AngularJS is a nice JavaScript MVC setup. So I've got my views, which are the HTML files, and my controllers are written in JavaScript. So all I've got here, this is the view dinosaurs. So I'm going to call a get to my dinosaur service. And then in create, I've just got a form here. So it allows me to enter the name and the era and whether or not it's carnivorous. And then just because it's easy, in the view page, I've added the ability to search using some of the JavaScript libraries that AngularJS allows. So we'll check that that's running. I think it was 8,000. Perfect. There's my dinosaur app. So let's give it a go. Create a dinosaur, Tyrannosaurus, possibly Cretaceous, who knows? Was it a carnivore? Yes. Go. Oh, creation failed. So if we have a look at what's actually happened, I've got it on a slide to make the text slightly bigger here. Cannot load, no access control, allow origin header present on the request. It's not a Mac. We found cause. We found the same origin policy, I should say. So what is this? Why was it introduced? This is something that the browser is complaining about. It's saying, well, you didn't tell me that I needed to speak to localhost 8000 and 1992. So, you told me you were coming from localhost 8000. Therefore, because you're talking to this other one, I think you're a hacker, and I'm not going to let you display this code. What I would actually have to do to get around this is I will have to go back to my server, and I will have to say to the server, oh, no, it's OK. You can allow this guy, localhost 8000, to talk to you. So the code change on the server that I would have to make is I'll have to add in some headers here. So my server, when it replies, will have to say, yes, it's OK to allow someone from localhost 8000 to talk to me. And I will also have to say which headers they can send as well. So I'll save that and let typesafe recompile it. Oh, it's died, doesn't it? Right one. Yeah. So the reason that the same origin policy was introduced is sort of in the early days of the internet, when browsers really did have a lot of points for hackers to come in. They could do things like if you sent a request and they had some JavaScript running. Oh dear. Anyway, you can imagine that it does work. Now I've got the headers in. Let me see whether I can restart that. Was it here? Yeah. Let me go back to my slides. If it does work later, we can have a look, but it's not that interesting. So what it's saying is I have to make a change on my server side because the client is complaining about talking to me. And this was built into browsers to try and protect them from the number of weak points and hacks that browsers represent. To put it in better terms, opening an XML HTTP request is the point that allows these cross-site forgery attacks. You can send data in from a source other than your original source. And Cause provides a workaround by which you can say that the server can say that it allows the client. one of the first things I was taught when I was learning about service-oriented architecture was not to build in these dependencies, particularly not to build in a backwards dependency, whereby you're saying every time somebody builds a new client that wants to talk to my server, I have to go and change my server to allow this client to come in. Okay, I understand that there were big security issues and they needed to get something out, and the browser was the point at which the weaknesses were happening, so they put this into the browser. But now, us in the future building, Scala apps with JavaScript front ends, we're bumping into this, and I imagine what everybody does on the server side is just say allow origin everybody, because you can use a star character to say everyone can come in. So the same origin policy isn't really adding much protection. If you want to secure your service, you should be using HTTPS. You should be using, HTTP-based security methods. You shouldn't be using this kind of same origin policy hack. And I'll go on to the next slide because I'm talking about the complaints here. Thinking about cloud architectures, if you're saying allow origin from Amazon Web Services, that isn't really increasing, your security. But I think how this links back to my concepts is that, it's something that we built in, and now we're stuck with it, and we're not really losing it because it's too difficult to get the browser people to change. It's not in the HTTP standard, this same origin policy, but it's just something that browsers that we're used to do use. And for that reason, I'm branding it as Vestigial Functionality. It's there because it was rushed in to try and fix these security problems with browsers, and it really isn't something that fits in modern architectures. It gets in the way. We have to use this CORS workaround. It's definitely a piece of vestigial functionality. Okay, on to our next likely piece of sand to dig. Soap. Do you remember when XML was new and exciting and everyone was saying, wow, we can nest structures and we can still have attributes, and then SOAP was invented, and SOAP was going to be the cross-platform communication of the future, and everyone was going to talk to everyone else. And the foundation for web services. So you had this XML-based structure. It was flexible. You weren't tied to one protocol. It's like, well, you can use HTTP or TCP. And then specifications rose up around it. So you get things like WSDL to Java, which means you can take a definition and have your client code generated with one click, and then you can talk to a Microsoft machine with one click. And everybody built SOAP services, and we're still using them now a lot. But again, I'm going to try and do a demo to show how SOAP has not really quite lived up to the expectations of its designers. And for this demo, what I want to do is get a Java web service to talk to an ASP.NET web service. So we'll start with the Java one, if I can get it to run. So for this, I'm going to use Apache Axis. This is based on a real experience that I had. It's slightly contrived because the version of Axis that I'm using is a fairly old one, but there are still web services using this version of Axis today that you may well need to talk to in some of your architectures. So, it's still relevant. It's very easy to write a web service using Axis. All I need to do is define my interface, my method. And what I want to do is, given an XML definition of a dinosaur, I'm going to extract its name. So I'll create my bean, which uses the annotation to say that it's going to be a web service. And I'll just put in some random method implementation that takes the XML and figures out the dinosaur's name. So if I can start this, I think this one. Missed it here. And then we should be able to see that Axis has exposed that. If I can remember what port it is. 8092. No. Let's have a look at the logs. 8019. So here's Axis running, and here's my list of services. And I can see that my dinosaur namer bean is now a web service, and if I click on it, I've got the WSDL definition. So now I can go across to the world of Microsoft. I can start a new MVC application, Microsoft has a nice way of representing MVC. So you have your model class. It's called home because I just used the default that you get. So I just got a dinosaur name property. And then your view is your HTML. And so I'll just display it using the nice Razor syntax. And then I've got my controller class, which is what will run when I hit the index page. So what I want to do here is I want to link through and get data from my Access service. So I'll add a new service reference. Add the WSDL. It should find it with no problem. I'll call it a dinosaur namer. And that's all I need to do. And now .NET will have built for me a client API that should allow me to then just reference through to this dinosaur namer. So instead of name being an empty string, let's call the service dinosaur namer. I want a client. Now this needs a string, which is the name of the client. So what .NET has done is in the configuration file, it's created the reference back. And there's a name in here that I need, this one. And while I'm here, I'm just going to change it to reference localhost rather than the port. And then I should just, oh, I forgot the new. I should just be able to use this client API to figure out how to call it. So it's name dinosaur, yeah. So what does that need? It needs a new one of those, yep. Which has a name, yes, this is good. Equal to a new node, if you say so, which has a, okay, now I'm really a bit stuck. It's created me this beautiful client API, which is practically unusable. Okay, that looks like a string. Give that one a go. Oh, did I not? Oh, of course I have to define a value for it, don't I? Dinosaur. Okay, it compiles. All right, let's run it and see what happens. This is how Microsoft developers work, I know this. Great, seems to be running. Oh, fell over. Let's go and see what it's complaining about. Some kind of exception here. Oh, fault exception. So let's go and see what Access has to say. Not that one, this one. Instantiation exception. So Access could not build the XML node from the data sent by .NET. So what we'll do is we'll put a breakpoint in our .NET code. So we can do this by adding a message inspector that we can hit this breakpoint before we send to see what we're going to send to Access. So I think I just need to add endpoint and point behaviors dot add new inspector behavior. Oh, okay, so let's see if we can catch what we're sending. Did you see that? Close your programs. You're running out of memory. But before we run out of memory, let's have a quick look at what we've sent. Oh boy. That's not a particularly good representation of our dinosaur string. I'll just kill it before my computer dies. But the point being is that the ideal there was that we had this beautiful cross-platform architecture that would allow these two different beast to speak, whereas in reality, the definitions were not quite tight enough, and the two were completely incompatible. The main reason for it was that I'd passed in a Java class as a parameter, and .NET had tried to build a representation of this entire Java class. Future versions of Access won't let you do that, so you don't come across the same problem. But we did come across this real-life problem when we were building at Capgemini. So SOAP, what are its problems? I see it as a monolithic solution. It started off as a good idea for slightly more lightweight than RPC, talking cross-platform, and it's ended up trying to be all things to all people. And actually, because of the way that it's extended, has ended up not really living up to this. I was lucky enough to attend a talk by John Newton, who he was a founder of Documentum, and he was talking about REST sort of in the early noughties, and how REST has come up from what's actually been used, whereas SOAP is coming down from a well-meaning committee trying to write for what they think people want. Whereas REST is based on the internet, which is what has been actually working for years, and SOAP, the people who wrote the definition, are obviously incredibly talented and clever and know a lot about how the internet works, but it's that difference of like a well-meaning committee versus things that have evolved because they're found to be useful. So for that reason, I'm branding SOAP as outdated as a dinosaur, because there's been a divergence to microservices, and this monolithic architecture is not really necessarily what we want in our architectures today. And then the final piece of sand to dig through is EJBs. I had a quick look at the EJB specification, see what they're trying to do. Persistence, transaction integrity, security, concurrency, events, asynchronous calls, tea-making, world peace. You might as well. Each one of those topics is enormous, and they've tried to write a specification that covers all of this in order to make life more simple for developers, whereas in fact all they've done is increase the muscle power of developers' arms as they try to lift the specification, because if you can understand the spec of this, then, well, you're a better developer than me, and I don't think many people, even who dedicate their lives to it, have really benefited from the task that the EJB designers set out to achieve. EJB 3 is much better than EJB 2, and that it seems to be quite heavily influenced by Spring. And again, Spring has come up because it's been useful and been used, whereas EJBs has been designed down to meet it. So I think, again, that follows in the same kind of monolithic versus up from use from the internet kind of direction that I've been talking about. So yes, it's known as the golden hammer. You're trying to obfuscate all this complexity, but is it actually a good thing? Each one of those topics ought to be discussed. You can't just say we're going to use EJBs to solve all of those problems. And there will always be something it doesn't cover. However hard you try and define a specification, the environments are going to change and adapt and extend beyond your specification. So is there any point in even trying, I think? For that reason, I'm designating EJBs as a dinosaur. We're moving to microservices where we're working with the minutiae. We're trying to understand and not obfuscate the complexities of what we're doing. So a quick summary about what I've been saying. There have been two themes. There's been this theme of divergence. So we've seen that we've moved away from these monolithic committee decisive solutions and away from trying to future-proof things. If it's not in your specification, then don't build for it, because the thing that you're future-proofing against, you'll probably guess wrong. And towards simpler and more modular solutions. And this has been driven by changes in hardware and software, particularly changes in networks that are allowing these communications between the smaller pieces. And by the fact that the monoliths are not living up to the expectations that the designers had for them. And the second theme that we looked at was vestigial functionality. I've put here the two types as controllable and uncontrollable, because things like the singleton, you can decide whether or not to use it. But things like whether or not a browser implements cores, I think is going to be, implements the same origin policy. We can't really control that as easily. And why have we ended up with this functionality? Sometimes it's our own fault. We just do things because we did them before. That's how humans work. And sometimes it's because we're working with something that's too big for one group to change it straight away. Takeaways. I struggled a bit with this slide. Not to say what is the point, but could I predict the next dinosaur? I don't think I could. No, I mean, last time I did this talk, somebody said JavaScript is going to be the next dinosaur. It's a house built on sand, you know, but I don't know. So I think, you know, what we can say is as we're designing our code, be aware that you're designing for today. So maybe it's not worth even trying to design for tomorrow because you don't know what tomorrow will bring. Don't try and future-proof your apps. Just work with what you've got. And another thing I was thinking, well, maybe you should design for disposability. I mean, I know that most of the code that I've written in my life, because it's in web-based architectures, it's related to business processes, none of it will be around more than 5 years. But then that's just because of the area I work in. I gave this talk at Birmingham University, and the guy after me was talking about the Heartbleed Virus, which is fascinating, and that the bash kernel shell code that the virus was found in is 40 years old, and there's no need or reason to replace it. So it's not about the age of the code. It's not that you need to design for disposability, but I think it's just to be aware of the environment that you're designing for, because in summary, things will change. So yeah, not a insight into the future, but a warning. Thank you very much for listening. Is there any questions or comments or thoughts?
If you could remove any one of those from history, which one would you remove?
I think it would be EJBs. Then I wouldn't even have to try and get my head around any of the versions.
It's kind of interesting with EJBs, and so you said that things were well-intentioned, and I think the thing that kind of defines those technologies that were actually, I would say, probably not well-intentioned, in the sense that software cabals kind of got together to make something so complicated that you have to use their infrastructure and their tools.
That's a good point, yes, yeah.
You know, I think SOAP and EJB are complex, so they're complex.
It's an evolutionary power of the companies behind it to keep people going in them, yeah. Yeah, no, that's a very good point, yeah. Not really looked at it from that angle.
So which of these mistakes are we making today without realising it?
Well, all of them, I think. It depends where you're working. I mean, if you're in an object-oriented mindset and you're writing functional code, you can make them. If you're an architect and you're designing for a big system and you've always done the same thing, then you know it's time to step back and review it. It depends the area that you work in, really, because we'll probably all work in very different kind of areas. So, yeah, all or none, I don't know. If there's no more questions, I'm out of time. So thank you very much for listening.